If you're regularly watching my videos, which by the way I highly recommend, you already know that I have a new machine and entered the CNC era. Namely the CNC era of the 1980s, but anyway. The machine I got is a benchtop CNC lathe from the Austrian company Emco. It was built back in the days for educational purposes. On my particular machine there were some things which I wanted to fix before doing real work on this lathe. Some of the issues were design flaws right from factory, some were defects, and some were both. One of the more obvious things I wanted to address was the immense amount of play in the lathe saddle. It was clearly noticeable by feel and eye, and the dial test indicator confirmed a play of about 0.2 of a millimeter. That's definitely too much. So this will be the first thing I want to fix on this machine. For this, I had to disassemble the machine at first. I started with removing the tool turret and then removed the X-axis stepper motor to further disassemble the lathe cross slide. With the cross slide out of the way, I can remove the X-axis ball screw assembly. This will be modified as well later in the video. Here again you can see how much the bed slide wiggles. The tailstock has to be removed too. To reach to the underside of the lathe carriage for further disassembly, I had to unscrew the whole lathe bed with the headstock from the chip tray to be able to tip the lathe bed over for reaching the underside. The lathe bed is mounted with 2 bolts to the machine base. With these 2 bolts removed, it is possible to rotate the lathe bed about 90 degrees to reach the underside. I supported the right end of the bed with 2 pieces of wood to secure it in position. Now a new problem comes into sight. The mounting block of the C-axis ball nut is only made out of plastic and it is already broken on one side, right around the mounting screw. Here you can see the, I guess, cost-efficient way Emco designed and built this machine and the purpose of only being an educational machine for learning the basics of programming G-code instead of being a real production machine. So this has to be fixed too. Now I can reach the mounting screws of the saddle gips strips, which have to be screwed out in order to remove the saddle from the lathe bed. The previous owner of the machine had already replaced the original gips strips, also made only from plastic, with some new ones out of brass. But sadly, he didn't take care about the correct fit and built the whole thing with massive play in the carriage. So my plan is to replace the brass gips strips with ones from cast iron and properly machine them for perfect fit. With the bare saddle of the lathe on the bench, the next thing to be fixed gets clear. None of the slideways have holes for lubrication. Another design flaw which I want to address. My plan is, with a clever arrangement of holes, to bring oil to all the sliding surfaces, including the dovetails of the cross slide, the main bedway sliding surfaces and the gips strips. Before doing the machining work on the bed slide, I removed the remaining way wipers and sheet metal cover. For the new gips strips, I ordered a flat piece of cast iron in the right thickness. I started with cutting 2 pieces to the right length on the bandsaw and sawing the strips to the right width on my milling machine. With a 6mm carbide end mill, I machined the new gips strips to the exact width. Now I drilled the mounting holes and one smaller hole from the side as a channel for lubrication. On the side, which slides against the underside of the lathe bed, I milled a small groove for oiling with a tiny 1mm ball nose end mill. The hole drilled here connects the oil groove with the porthole I drilled from the side previously. And these are the two semi-finished gips strips. One end of the porthole gets closed with a small M3 set screw. The oil enters the gips strip through the larger hole, flows through the small hole to the side, and exits right in the oil groove. To finish the gips strips, I decided to scrape the sliding surfaces in. For this, I blued up my small surface plate and gently rubbed the gips strip over the surface to mark the high spots with a blue ink. Now I know where I have to scrape away some metal to make the part as flat as possible. A carbide hand scraper is used to manually remove the high spots. After dozens of passes, the strips are reasonably flat, which you can more or less see on this sliding test here. And these are the two finished new cast iron gips strips. Now I had to modify the mounting surface for the front gips strip on the lathe saddle. This was the side which had too much play. I carefully aligned the saddle on the milling machine and took a very light cut to bring the surface slightly lower. I also made a relief cut on the rear slideway and tried to scrape the sliding surface in relation to the lathe bed, but after a few strokes I realized that my hand scraper is too big for the tiny surfaces, and I decided to set aside this task for a future project. As said, the saddle in its original state had not a single port for lubrication. So I decided to modify it and install some lubrication channels. After a little bit of brain work, I came up with an idea of using only 2 lubrication points and, with a clever arrangement of drill holes, feed all sliding surfaces of the saddle with oil. Two long holes will go deep into the saddle to feed the different outflows to the sliding surfaces. Some exit holes direct the oil flow to the sliding surfaces. On the dovetail of the cross slide, I need 4 outlets to feed oil to the 4 sliding surfaces of the cross slide. 2 on each side. I started with drilling the 2 extremely long 2mm holes from the back side of the saddle. One of the holes feeds the rear sliding surface. A small hole in the exact position connects the rear sliding surface with the feeding oil line underneath. The compressed air test shows success. Both holes correctly align with each other. These holes will feed the oil up to the dovetail sliding surfaces and also to the gips strip. For the outlets on the front V-way, I started with a small end mill before drilling the holes all the way through with a small drill. And again, these two holes successfully align with the feeding oil line underneath. Now only the cross-slide dovetails remain. Both sliding surfaces get an outlet for the oil. One of the holes has to be critically precise in the exact angle to connect to the feeding line. This was quite nerve-wracking, but I managed to perfectly match the two holes. Both holes couldn't match better than this. As a last step, I had to mill some oil grooves to distribute the oil over a larger area of the ways. I did this in a zigzag pattern to evenly lubricate the sliding surfaces. And this is the finished modified saddle with all the lubrication lines and oil grooves. For testing the lubrication system, I temporarily mounted the gips strips as they seal some holes and have outlets for lubrication too. Finally, I installed the two oiling ports. Don't be worried, the position is not the final one. Now I had to fill up my new oil gun at first with 68-way oil before I can test the new lubrication system on the saddle. It seems that there is oil on every outlet, which is a good sign. Of course, it's not said that every oiling port gets the same amount of oil, as the oil is distributed from only two feeding lines, but it's definitely better than the original state without any oiling port, I guess. Next, I removed the Z-axis ball screw and nut for fixing the broken ball nut mounting block. My plan is to replace the entire broken plastic part with an aluminium one. The ball nut on this machine is two-parted to adjust for minimum backlash. With the retaining screw removed, the loose part of the ball nut can easily be unscrewed. To completely disassemble the ball nut assembly, I first had to remove the loose bearing on the spindle's end. As said, the ball nut consists of two parts. The loose part can just be unscrewed, the other part remains in the plastic mounting block. As there are a lot of tiny steel balls inside the ball nut, I inserted a drill bit in the right size to not lose any of the balls during disassembly. And this is how the ball nut looks inside. You can see the tiny bearing balls which rotate inside the nut. As I didn't know it better, I first tried to press the ball nut out of the plastic piece until I noticed that it is actually screwed in. I took a piece of aluminium with the right dimensions and cut it to length on the bandsaw. This thing will replace the original plastic bearing block. On the milling machine, I brought the part into its desired shape. To drill the big hole for the ball nut, I chucked the part up in the forge-up chuck of my lathe and drilled and bored out the hole to final size, and also cut the thread for the fixed part of the ball nut. On the drill press, I drilled 2 holes for mounting. A nice chamfer finishes the milling work on the part. And that's the finished new made ball nut mounting block from aluminium. For adjusting the nut for minimum backlash, 2 threaded holes are needed, which secure the floating part of the ball nut. This hole with an M6 thread will be the inlet for the oil. The new mounting block gets an oil port too. Again, the original one had none. To bring the oil from the oil port right into the middle of the 2 ball nut parts, again, a small hole in a specific angle is needed. This time I needed a second attempt. I screwed up the alignment of the first hole and had to drill a second one. Now the Z-axis ball screw assembly can be put together again. Putting the ball nut back on the ball screw can be a little bit tricky, as you see here. One tiny steel ball left the ball nut and had to be placed back. These spring washers preload the ball nut assembly and eliminate the backlash. This small screw adjusts the correct preload and backlash. But before installing the ball screw back on the lathe, I first modify the lathe cross slide. This part too has no oil port for the X-axis ball screw. At least the ball screw mounting block is already made out of steel right from factory. I just had to disassemble the whole thing and drill some oil lines to feed oil to the ball nut. A long hole from the backside of the cross slide feeds the oil directly to the ball nut mounting block and through a small hole into the block. Again, I checked with compressed air that both holes align. The ball nut mounting block has to be drilled too, and again, an angled hole is needed to bring the oil directly into the middle of the two-parted ball nut. Now I can reassemble the ball nut and the cross slide again. A small piece of aluminium foil will act as a seal for the oil inlet. If I've done everything right, the oil should be directed through the cross slide and directly into the middle of the two ball nut parts. Before installing all the modified parts back together on the lathe, I firmly cleaned all parts and the lathe bed from old grease and gunk as best as I could until the bright yellow color came back. I started with reinstalling the lathe bedslide. As it was a little bit too tight with the new gib strips on the front V-way, I had to shim the gib with a little bit of aluminium foil to get the right amount of play for the bedslide to slide freely on the bedways. Obviously, I removed a little bit too much from the mounting surface of the front gib strip. But after a little bit of fiddling around with the aluminium foil, I managed to get a good fit on the bedslide. With this done, I reinstalled the C-axis ball screw and connected the new made ball nut mounting block to the bedslide. I also renewed the old felt on the C-axis ball screw wipers. Now I can mount the whole lathe bed back to the base plate and continue with remounting the lathe cross slide. A few strokes with the oil pump to check if the lubrication system works and to make assembly of the cross slide easier. And now the moment of truth. I checked with the dial test indicator if the new gib strips improved the fit on the lathe saddle. I measured less than 0.05 of a millimeter of elastic deformation. I think that's fine. Now I can bolt the lathe bed back to the machine base. The old felt-way wipers also got renewed with small pieces of fresh woolen felt. Originally, the felt was held in place by a small piece of sheet metal. As I didn't like that, I made small aluminum housings for the felt-way wipers. Another thing I wanted to install on the lathe before machining the first parts was some sort of protection for the machine's bedways. So I made a solid way cover from pieces of stainless steel sheet metal, which gets attached to the lathe bedslide and is held in place with magnets on the left side. As this part may be interesting for others, I made a whole video on making this stainless steel bedway protection, which you can find on my channel. To use the machine later with some sort of Lathe coolant, I had to drill a set of holes which act as a drain. To redirect the coolant back into the system, I had to drill a hole through the side of the machine base and made a block out of aluminium which connects to a hose mounting fitting. One last thing I wanted to fix on my machine was the defect cassette deck. It was used back in the days to save and load programs to small data cassettes. On my machine, the pre-owner removed the cassette deck for an additional control panel as he upgraded the machine controls with some additional features. But I had the wish of bringing this old-school saving device back to life. Normally, the cassette should make a few turns when the machine is started, but in my case, nothing moves. So a friendly colleague sent me the replacement parts of his similar machine for error research. After confirming that the new parts work as expected, I did a few measurements on the electronics and ordered some replacement electronic parts. Some parts on my circuit board look a little bit suspicious. So I removed and replaced some of the electronic components and, to my surprise, with the help of my colleague, somehow managed to bring my defect circuit board back to life. But the success was not for very long. There seems to be a major error in the electronics or the programming of the machine, as it was still not possible to save and load programs from the cassette. Every time I tried, there was an error message on the display showing that loading or saving didn't work. With this message on the display, it wasn't possible to continue. The machine was completely frozen and I had to press the reset button to start again. So if anyone has an idea how to finally fix this problem, I would be very thankful for your help. And now it's time for machining the first part on my new CNC lathe. As it is a 40-year-old machine, it cannot communicate with today's CAD/CAM software. So you have to program every part completely by hand. Originally, this was only possible via the keys on the control cabinet of the machine. There actually was a different version of the machine, which needed a computer for programming instead of the control panel on the back of the machine. This version used a special CAD/CAM software, which I actually have here, but sadly couldn't manage to get it to run on my computer. So for now, the only way of making programming the machine a little bit easier is to use a G-code editor called Mike's Free Interface. You still have to type in every line by hand, but programs can be saved on the computer and loaded directly from the computer to the machine. In addition to that, there is a simple graphic simulation which allows you to check the program for major errors. For the first test piece, I programmed a game piece for the game classic Mensch ärgere dich nicht, or in English, Man Don't Get Angry. To send the program to the machine, you just have to connect the computer with an RS-232 cable and press the according button on the machine. But before running the program, the cutting tools needed must be installed at first on the lathe tool turret. When you need more than one tool for the part, which is the case here, you have to measure each tool in to compensate for the tool offsets. For this, Emco offered an optical measuring microscope back in the days. As I don't have this item, and it is even on the used market extremely expensive, I went for a digital microscope with digital crosshair. This thing works so well and is so convenient to use that I don't miss the original optical microscope at all. And now we can start with our first demo piece. I chucked up a piece of blue 12mm round plastic bar in my self-made ER20 collet chuck. And now we are ready to start the program. I leave the machining sequence in real time for you. The tool changes are a little bit too slow for my taste, but yeah, it's an old machine. And here we are, the finished self-made game piece. It took me quite a lot of failed test pieces to get to this point, but the end result looks pretty okay, I guess. So I hope you enjoyed this episode. Thank you all for watching, and till next.